Okay, so ladies, what we're going to do is we're going to talk about a concept called relative velocity, okay? Which is looking at...
May I have your folder?
Looking at...
Thank you.
You're welcome. It's looking at, like basically if you were an observer watching something traveling through a medium, what would it look like to you? Because what it would look like to you might be different than what it would look like to somebody else. That's what's meant by the concept relative. Relative means to something or someone it may look different than to something else. Give me an example. Right now you're moving relative to the person beside you. You're not. But if I was on the moon watching you, which would be creepy, you would be moving relative to me. So relative to someone else you might not be, but relative to me you are. So this concept, relative velocity, is actually quite easy. We're going to look at just really three variables, okay? And they're illustrated up here. So this is an equation which says VOG. So what is VOG? VOG is the object that you're looking at relative to the ground. It has a velocity that is the sum of two things. One is the object's velocity relative to the medium that it's in. So the medium that it's in could be water, it could be the air, whatever it's traveling through, that's the medium. Okay? Plus the velocity of the medium itself. So I'll give you an example. Okay? Very, very simple example. Imagine that we have a current, okay, and the current is traveling 2 meters per second to the west, and then we have a person there's my person, in the water traveling 2 meters per second the other way. Now, if you were in the river with this person, it would look like you were moving. But if you were on the shoreline watching this swimmer, what would it look like to you? They weren't moving at all. Because when you add up the object in the medium, which is the swimmer in the medium, which has a speed of 2 meters per second, with the speed of the medium, I should say the velocity of the medium, which is 2 meters per second the other way, that adds up to 0. So to you, relative to the ground, it wouldn't look like you were moving. Not you, sorry. The swimmer would look like they were stationary. So we're going to apply this concept to this question with a swimmer. Okay? So we got a swimmer traveling north. So what would that look like? So let's draw a river. So here's my river. So there is the shore. There is the other shore. Okay? The swimmer is going to go and start off traveling north. So their velocity would look like this, which is 4 meters per second. Now imagine that there was no current, okay? Then that would be the end of the story. If you were on the other side watching the swimmer, they would look like they were coming directly at you. But if there is a current, you would see something. You would see now that the swimmer would actually be traveling on an angle. Now why? Well, because the current has a velocity which is 3 meters per second to the west. So what do you think it would look like to you? What would it look like to you? What would it look like to you? It would look like they were traveling north towards you, but it would also look like they were traveling west. Why would they be traveling north? Because the swimmer's velocity is north. But why would they be traveling west? Because of the current. Now, how do you add these two vectors up? Well, you do what we did before. You do the xy component method, right? So remember the x and the y are independent. So the swimmer, we're going to label the swimmer as the object in the medium, and we're going to label the current as the medium relative to the ground. So let's look at the vector for the swimmer. Okay? which is the object relative to the medium. If you had to give that a coordinate, what would its x value be? 0, right? So that would be 0. What would its y value be? Plus 4. Okay. Is this anything different than what we've done? No, right? Now look at the current. So I would give it -3 because it's west, and 0 because it's neither north nor south, right? Now when I add these two vectors up, or these components up, I get my velocity of my object relative to the ground. And let's see if it makes sense, okay? What would the x result be, or resultant be? So -3, and the y? +4. So that makes sense because it would look like this then, right? It would look like, let's use a different color. Let's use green. 4 this way, 3 this way, right? So this is what you would see, this right here. That. And that makes sense because it's pointing north and it's also pointing west. Now those are the components, but what would the actual, if I had a radar gun and I could measure the speed, what would it look like? What would you do? So this is 4, this is 3, we do the sum of the squares, right? So we say the object relative to the ground is the sum of 3 squared plus 4 squared. So what would that speed be? Well, that's a 3, 4, 5 triangle. So that should be 5, right? And if you don't believe me, you can check it out. Now, you would see, so if you were on the shoreline, not moving, you would notice that this swimmer would be traveling at 5 meters per second. But because of a velocity vector, we need a direction too. So how would you do direction? What would you do? Considering that the 4 is the adjacent side and the 3 is the opposite side, how do you get direction, if you remember? You could use inverse of what? Yeah, inverse tan of opposite. Sorry, yeah, opposite over, which is 3 over 4. What would that give you as a direction? What's the angle in a 3, 4, 5 triangle? So what would that be? What's the inverse tan of 3 over 4? 37 degrees? That sounds about right. Okay, so how would you report this answer? You would say the velocity of the object relative to the ground would be 5 meters per second. We'll say north, 37 degrees west. Okay, this method that we used, is it any different than the method for displacement or acceleration? I mean, acceleration, you were subtracting the vectors because, you know, it's VF minus VI. It's no different, is it? Same method. Fiona?
How do you know put the north and the west? Why is north come before west? Because not.
What is north come? Okay, so it's in the direction that we're going. So here's my angle, right? This vector is the one that's pointing which way? North. So I start with that one. So I start with the vector that's pointing directly north, west, east, or south relative to my angle. So here's my angle over here, and that vector is pointing north. So I start with that one. Okay?
So why would you use inverse?
Because we're looking for the angle. Normally we have the angle, we want the component. Here we have the opposite. We have the component, we want the angle. Okay? Now, what happened here? Cortana is trying to rear her ugly head. Okay. Now, let's look at the second follow-up question here. How long does it take to cross the shore? Oh, I got to tell you how wide the shore is. That would be important, right? Okay. Let's say that the shore has a length going north. Let's say of 400 meters. Okay? Let's say it's 400 meters across. So from where they were here to where they end up is 400 meters across. how long would it take to get across the shore? So time is distance over what? Okay. Or distance over velocity, right? Displacement over velocity, but in this case it's the same thing because we're going one direction. All right, what's the distance? Okay, 400, right? And that's 400 meters north. Now, what's the speed, or in this case, the velocity? Do we use 3? Do we use 4? Or do we use 5? What do you think? The question is asking you, how long does it take to cross the river? Well, we got to assume that the speed here is constant. Emily, why would you use 4? So across means which way? Which axis is across? Y-axis. So remember, the x and y are independent. So if I want to know how long it takes to get across, that's which axis in this question? Across would be just the y-axis. So I got to use the velocity of points along the y-axis. In this case, it would only be the swimmer's speed relative to the water, which is 4. So it would be 400 over 4. Now, that will give us 100 seconds. If the question was, how far does the swimmer travel? That's a different question now. How far does the swimmer travel? Then it would be from where they started to where they end up, which would be in this direction. Well, what would you use that case? You would use 5. If the question was, how far downstream are you? In other words, you're supposed to be here, but you end up over here. Then what would you look for? You would look for this component. So then you would use that speed. You would figure out how long it takes to get across and multiply it by 3. Okay? So it always depends on what you're being asked for. And remember the big idea. X and Y are? All right, you got nightmares about that. Okay, now last question. Okay, last question. What if we wanted to get directly across? All right, so what if we want to go directly across? Now, I'm going to do something that's wrong, okay? And you're going to tell me why it's wrong. So if you remember the previous example, the swimmer went 4 meters per second north. The current 3 meters per second west. And this was the resultant speed, which is 5, right? So why can't I just take this triangle and flip it? If I take this triangle and flip it, I get 5, 5, 4, 3 triangle, right? Correct? And if I do this and I say, okay, what if I had 5 meters per second in north 37 degrees east? Because we know this angle is what? 37 degrees. So what if I say, okay, let me go 5 meters per second north 37 degrees east. The current will push me back and I'll go directly across. That may sound like it works, but there's a problem with that. What do you think the problem is? Read the question. Max speed is 4. If I do this, what's my speed in the water? 5. I'm going faster than I can possibly swim. So I can't do this. So how do you solve this question? Well, this is what you do. We know we want to get directly across, right? So we know that we want to go this way. We know there's a current that's going to push us this way. And we know what the velocity is too, right? We know it's 3. Correct? So what do we need? We need this. Correct? What angle is this? Okay. Now, we're going to assume that their maximum speed is 4. So that is the actual speed of the swimmer. If they travel at some direction, north of something east, at 4 meters per second, the current will push them back and will go straight across. So this, okay, we know what this is. This is the medium relative to the ground. What's this?
Sorry to bother you. They say that I didn't have it in your period D. Will you give me period D? 4. Thank you, sir.
You're welcome. What's this velocity? This is the object relative to the medium. This is relative to the ground. Because this will be the sum of this and this. If I go north something degrees east, the current will shove me west and I'll go straight across. So that's a right angle triangle. So can I get this VOG using Pythagorean theorem? I can, right? So how would I get it? Well, it would be 4 squared minus 3 squared. So what is VOG? What is it? Sorry? Can't be 7. It's got to be smaller than 4. Which is 2.6. Okay. And so if this is 2.6, now if I want my angle, I can do the same thing I did before, right? I can take the inverse of 3 over 2.6. What would the angle be if I did that? 49? So this says if my speed is 4 meters per second north, 49 degrees east, the current will slow me down, the current will push me to the west, and in the end, I will travel directly north with a speed of 2.6 meters per second. Okay? Got that? Sure? Yeah.
Why is it east?
Sorry?
Why is it north 49 degrees east? Where did you get east?
Well, what's this? North? So this east, this way, right? Because the current's going to push me west. So if I start traveling this way, the current will slow me down, and it will push me to the west. Okay? So let me stop there.